Hello and welcome back. In this lecture, we learn about the concept viscosity of a fluid. Viscosity is a fluid property. To better understand this concept, we have reviewed several sub-concepts in the previous video. Please make sure that you understand those sub-concepts before listening to this lecture. To better understand the concept viscosity, consider a fluid flowing between two large parallel, stationary plates. The no-slip condition implies that velocity of fluid at the plate surface is zero. The velocity gradually increases towards the center where it is maximum. We can imagine that the fluid has a velocity distribution. The fluid velocity, u, at a given location, y, can be expressed as a function of this variable y, which is the distance from the center of the plate surfaces. Experiments indicates that the shear stress developed at an imaginary fluid plane is proportional to the velocity gradient exist in that plane. The constant of proportionality is called the coefficient of dynamic viscosity, denoted by the symbol μ. The unit of μ is Newton-second per meter square. Mathematically, μ is the ratio of shear stress to the shear strain. If the shear stress and shear strain are linearly related, such fluids are called Newtonian fluids. For such fluids, the coefficient of dynamic viscosity is a constant. For example, shear stress-shear strain relationship of various fluids are represented in this figure. The slope of each line is the dynamic viscosity of the fluid. The ratio of the coefficient of dynamic viscosity to the density of a given fluid is called its kinematic viscosity, represented as the symbol nu. The unit of nu is meters square per second. Consider a thought experiment. A fluid is flowing steadily between two fixed, parallel plates. The velocity distribution uy is given as a function of distance y, mean velocity v, and distance between the plates. For a given dynamic viscosity, mean velocity and distance, calculate the shear stress developed at the bottom of the plate. Also, calculate the shear stress developed at the central plane. In this problem, the velocity distribution is given. We can use the equation connecting the shear stress and velocity gradient for solving this problem. The first step is to find the velocity gradient from the given function. Then, find the gradient at the surface. Using the given values of mean velocity, distance, and dynamic viscosity, we can calculate the shear stress at the bottom surface as 96 Newton per meter square. For the second part, to find the shear stress developed at the central plane, use y equals 0 in the gradient equation. Substituting y equals 0, we get the derivative du by dy as 0 at the central plane. This means that at the central plane, the shear stress is 0. Let us do another example. The flow configuration is similar to the previous problem, but the plates are 1 centimeter apart. Mean fluid velocity is 1 meter per second. Calculate the drag force by the fluid on the bottom surface, if the surface area is 15 meters square. Since the velocity distribution is given, we can calculate the derivative of this function at y equals minus h or at the bottom surface. Here, the mean velocity is 1 meter per second, and the value of h is 1 centimeter. To calculate drag, first calculate the derivative of velocity distribution at y equals minus h. Using this, you can calculate the shear stress at the surface. Finally, multiplying shear stress with area of the surface, you get the drag force generated by the fluid on the surface. Here is another problem. Calculate the shear stress experienced inside a pipe when a fluid is flowing through it. We will solve this problem in class. Finally, we have a cognitive map developed for the concept viscosity. This shows that viscosity is related to shear stress and shear strain, which is the gradient of velocity. This will also help you to connect the concept viscosity to other basic, physical quantities you already know. Thank you for listening.